as quickly as possible. My computer is acting a little bit funny, but if my video freezes, I'll try and join from my laptop or something like that. So I want to thank the reading group for inviting me. This is amazing. I think that what you're doing here, reading papers over the summer and like learning some stuff over the summer, is like 10 out of 10. That's awesome. I wasn't doing that when I was an undergrad over the summer. I was like running around and having a good time. And I think that this is like a really cool opportunity to really dig in. And I'm glad for the opportunity to come and speak to you today. So we're going to talk about discrete probability. And we're going to talk about a particular technique called the probabilistic method. So when I was in fourth year, one of my favorite professors said, if I could do it all over again, I'd be a probabilist. That was his opinion. He did like really fancy computer stuff. And that's my opinion now. If I could do it all over again, I'd be a probabilist. It's like such a nice field. There's super duper cool things. In probability, there's all kinds of surprising results, like kind of like weird counterintuitive phenomena. The methods are super duper powerful. And if you're into computer science, you can get really super fast algorithms probabilistically. And this is like a really emerging and new part of computer science, is doing things probabilistically, where you like toss some coins. And we're going to see a couple examples of those kinds of things later on. Has anyone taken a class that has a lot of probability in it? Does anyone take like stats 1 or? No. High school stats? Okay, cool. Yeah. Second year stats? Okay, all right. So some people have seen some stats. We're going to give an introduction to 107 and 256. Okay, nice. Yeah, we're going to give an introduction to probability. So if you haven't seen it before, that's okay. And we're going to focus in on a particular kind of thing. But I think one of the coolest things about probability is that it's just like, it's philosophically weird. Like, you know, we say that a coin toss is 50-50, right? If we take a coin, flip it, we say it's equally likely to land heads or tails. But like, what does that really mean about coin tosses? And how do we know that that number 50-50 lines up with anything in reality, right? I guess if we do this over and over again, it's eventually on average going to come out to kind of an equal number of heads or tails. But like, how many times do we need to do that for like to get this kind of convergence to a half? I don't know. I find randomness really philosophically challenging. I find it like a very weird thing. Because random events sort of seem to be like independent of history or something. It's like they have free will, or I don't know. Random events are philosophically super duper weird. And it took a really long time for people to get a handle on what randomness should mean mathematically. So like Leibniz argued that it was equally likely to roll a 7 on 2 die 6 is equal to 7. He said, oh, that's equally likely as 2 die 6 equaling 12. What? Right? Like Leibniz, like the best mathematician of Germany of his time, thought that these two things were equally likely. Right? And this is like a dude who is like as smart as Newton, arguing complete nonsense. Right? So it's easy to get this stuff wrong. And it took a long time to come up with a mathematical formalization of what probability really means. So we're going to talk about kind of two characters in this story of probability. So Andrei Kolmogorov was the first mathematician to come up with a mathematically rigorous theory of probability. He was working in the Soviet Union. He was kind of like one of the most respected Soviet mathematicians of the time. And he also did some sort of foundational work on computational complexity. We're going to talk a little bit about the computational complexity stuff. It's not the main focus of this talk, but it would be a cool talk to like come back and talk about Kolmogorov complexity. So Kolmogorov said a sequence is complicated if you can only generate it with a long computer program. So like a sequence of zeros and ones is complicated if the only computer program that generates it is like half its length or something. So that was kind of a notion of randomness, but he really laid the foundations for probability theory. And he did that in 1933. So that's really late in the game. That's less than 100 years ago. I see a comment, Shrivardhan saying, Erdős popping up everywhere. Yeah, man, Erdős is the man. He did so much cool stuff. This talk's going to focus more on Erdős's mathematics and how he used probability theory. And he introduced the probabilistic method in kind of like 1949-ish, 1940s, let's say. Huge groundbreaking method in combinatorics. And really soon after the mathematical formalization of probability. So as soon as mathematicians had a rigorous way of doing probability, they did all kinds of cool stuff with it. And we're going to see some of the cool stuff. So today, Erdős is going to be our MVP. He's going to do most of the heavy lifting for us. But I want to say how recent all this is. This is very, very recent math coming out of the 30s and 40s. Okay, so check it out. Which of these two sequences do you think is random? Just throw it in the chat. Yeah. One. All right, why are there no twos? Why does 2 not seem random? Unlikely. Yeah, it's alternating. Yeah, right. You know, it's weird to think that I would toss this coin and it'd come up, you know, tails, heads, tails, heads, tails, right? Like one and then the other. That's really weird, right? Yeah, it's an unlikely scenario. And thinking about that kind of Kolmogorov complexity idea. Come on, slides, let's do this. This sequence has a really short algorithm that generates it, right? It's just, oh, that should be xn plus 1, right? I just keep switching 0, 1, 0, 1, 0, 1, mod 2. Great. So this guy isn't random because it has like a really simple description. Right? There's a simple way to describe, you know, alternate heads, tails, right? It's got a short algorithm that produces it. And I think that a lot of the mathematical structures that we study have kind of these simple descriptions, right? Like, you know, the Euclidean algorithm, really simple, short algorithm that generates it. Or like the Fibonacci numbers, again, really short, simple algorithm. So the stuff that we can get at in mathematics tends to have really short descriptions, the stuff that we can get at explicitly, at least. Here's another example. Check out these two. Which one do we think is random now? Again, just throw a number in the chat. Yeah? Oh, now it's a little bit split. Too many T's. right? Okay, so check it out. Here's something kind of weird. This one also has a nice formula. In fact, it's a De Bruijn sequence. So Brian's going to tell us, yeah, right? So I'm not going to say what a De Bruijn sequence is right now. Brian's going to give that talk at some later date. But what's cool is that every possible pattern shows up. So like here's 4 H's, here's 4 T's, here's HTTH. Every pattern shows up somewhere in there. But that structure has a really simple description. It looks random to us, but it also has a really simple description. This one's actually the rando one. And to get it, I just kept hitting enter on my computer until it like looked weird. So let's see if I can pull up the code for that. No. Oh, there we go. Yeah, so this is some code. It generates random sequences. And as you can see, it's really short. It's a really short, simple algorithm just written in Bash, right? And it generates random sequences for me super duper fast. So one of the beautiful things about random stuff is that you can generate them very quickly and very efficiently on computers. They don't have nice algorithms to describe them, but generating random things is easy. Okay. So I just wanted to play around with that, check that out a little bit. Here's the like rules of probability according to Kolmogorov. So again, this is pretty recent stuff, 1933. And what do you have? You have a set omega of all possible events. So these are all the events that can possibly happen. And then you have some probability that says the probability of all things happening is 1. And the probability of a bunch of disjoint events happening adds up. We're not going to use these rules a whole bunch, but I want to just say that the rules of probability are quite simple. They're easy to write down, but they give us a very rich mathematical theory. So when we say a coin toss is 50-50, here's the kind of mathematical language that we're speaking. So our event space is heads or tails. Then we look at our events as being all possible subsets, right? So we've got like, you know, the empty sets in there. The set containing heads is in there. The set containing tails. Heads, tails, right? So our events are all possible combos of heads and tails. And then we're defining a probability. And we're saying the probability of heads is equal to the probability of tails is a half. So what this does is it gets rid of all the philosophical questions. We don't have to worry about physical coins anymore. We can just look at the abstract structure. Why do we have this? Right. That's a great question. So we need to be able to measure yeah, exactly. These are cool questions. What do these events even mean? So we need to have this rule that the probability of the whole space is 1. So we need to have the whole space in there, right? This is our set omega. And that event is like, if we wanted to give it like some like reasonable description, that would be like the coin lands either heads up or tails up. right? And of course, no matter what we do, it's going to land one of those ways. You know, we're ruling out the possibility that it lands perfectly on its edge, because that's like too crazy. And then the empty set is we do not flip the coin. Right? Nothing happens. We don't flip the coin. And we need that. We need these as events for kind of like a nice fleshed out mathematical theory, but they don't mean much in. But as soon as coin lands, coin becomes Schrodinger's cat. The cat is both heads and tails. I guess that's true, right? Right. It suddenly just becomes Schrodinger's cat all at once. Yeah, so that's what we mean mathematically by a coin toss. Okay, now there's these things in probability theory that are terribly named. A random variable. Okay, so weirdly, a random variable is neither random nor is it a variable. It's a function. Okay, so what this function does is it takes things in our event space and it outputs numbers. Okay, so given an event, we assign some number to it. And the expectation of a random variable is what we expect to come out of that variable. Has anyone seen this before? The stats people? Could we just get a yes in the chat? Yeah, okay. Yeah, expected value. Very, very, very helpful thing. I just want to say one kind of thing about this. This is kind of like an integral, right? You know how like integrals and sums are kind of the same? This is kind of like omega d probability. Okay, so it's sort of like you add up all of the values of omega as they're weighted by this probability. Okay, so let's just see an example for the folks who haven't seen expected value before. Let's say Parker and Brian are going to toss a coin. If it comes up heads, I have to give Brian $500. If it comes up tails, Brian has to give me $100. It's not a great game, but it's a game. Yeah, Brian wants to play, right? Why do you want to play? Why do you want to play this game? Yeah, Brian has a totally huge advantage, right? So our random variable here is x, which outputs, let's see, from Brian's perspective, or no, let's see, from my perspective, I lose $500. And then from my perspective, I gain $100. Yeah, so yeah, he wants to play because positive expected value, right? Brian wants, actually, wait 1 sec. I'm going to switch these signs. We're going to write this thing from Brian's perspective. Brian wants the expectation to be positive, and it is. Right, so we're going to put in our values of x. So we're going to get 500 times a half plus negative 100 times a half. Yeah, so on average, if we played this a whole bunch, on average, Brian would win $200. That's pretty good, right? Notice that that's not actually a value of the game, right? $200 doesn't occur here, but in the long run, if we played this many times, Brian would win. Excellent. Okay, so huge concept, very, very, very helpful with probability is this thing called the linearity of expectation. So the expectation, it's like an integral. Right? This is kind of like an integral, and integrals are linear. So what this means formally is that if we had a pair of random variables, x and y, we could split this thing up and just add up the expectation of x plus the expectation of y. So what this means is that we can decompose stuff in here into kind of like simpler parts. Very, very, very helpful tool. So I want to check out why this is a helpful tool. So let's say that we do a coin toss 100 times. And we're going to say how many heads should show up. So we make a random variable, right? Given a event, so given 100 coin tosses, we can measure how many of them come up heads. So what do? Okay, well, we take the number of heads. That's going to be between, actually, it's going to be between 0 and 100. Right? And then we say, what's the probability that there are that many heads? Okay, well, we're going to choose of 100 of those places. We're going to choose k of them to be heads. The probability that those ones come up tails and the probability those come up heads. Then we get something like this. WTF. What? That's like some like crazy contest problem solving stuff. Does anyone know how to evaluate this? Yeah, I don't know. Like take a Taylor series and take its derivative or something. So, okay, so expected values can get complicated. This is weird, right? But let's see what linearity of expectation can do for us. So suppose we toss a coin 100 times, how many heads should appear? Well, instead of just thinking of all the heads at once, we're going to split it up into a bunch of small parts. So we're going to write this as the sum of 100 random variables, where each one of those random variables just checks one thing. It just checks, is the kth coin toss a tails or is the kth coin toss a heads? So we're going to output 1 if it's heads and 0 otherwise. Yeah, so this is like an indicator function. So now we can use linearity of expectation. We take our big variable, x, and we're going to break it up into a ton of simpler things. Right, so boom, there's linearity. Each one of these super duper simple, right? We're just looking at a single coin toss now. Right? Half the time it's 0, half the time it's 1. So much nicer. So much nicer. Right? So linearity of expectation lets us split up this complicated thing into a bunch of really simple things. And this is like one of the things that you can do with probability is that you can kind of like, you can use it to evaluate those crazy sums, right? We had this. Right? And now we know that because these measure the exact same thing, we know that that crazy sum we had has to be 50. So that's a nice tool. That's like some like next level Putnam stuff. If you're able to take something and convert it into a probability question, you can often get an easier way of writing it or something. You can often simplify the question. but only works when you're in a really special circumstance. Okay. So now I want to share with you, actually just wait before we go on. Are there things people want to ask about linearity of expectation? Or expected values or anything like that? Yeah, Sachin, solid question. What? Sure, we can go back. And Srivardan, the slides are going to be available after the thing anyway. So I'm going to give these slides to Brian and he'll distribute them somehow. And then the recording will also be on YouTube, right? Yeah, so what does the expected value mean though? Sachin is a great question. This means what we expect X to output. So like if we do this experiment 1,000 times, right? We toss the coin a whole bunch and we take an average of how many heads show up. On average, we expect 50 coins to come up heads. Sometimes things might get weird. Sometimes we might get 58 heads, or sometimes we might get 42 heads. But if we keep doing the experiment over and over and over again, on average, it will come out to 50. So isn't this accurate if we flip infinite times? Yeah. And in the limit, that average converges to the expected value. Yeah, totally. Okay, cool. So now I'm going to let you in on the big secret. This is the probabilistic method. It says, and this is like pure magic, if the probability of something is not 0, then E is not empty. That thing actually happens. Okay, so if the probability of all the coins coming up heads is not 0, then there is some outcome where all the coins line up heads. But what this lets you do is like total magic. This is like the pigeonhole principle. Right? If something is big, then we get a conclusion. But for existence, huge mind blow. If we can show that the probability of something is not 0, then it actually happens somewhere. And existence arguments are often complicated, but this lets us do it just with counting. So we're going to see a couple examples. We're going to see one example of this. We're going to do it 2 ways. But yeah, this is the big tool, is this really powerful method for proving existence. And yeah, it's like a super duper simple observation. It just took forever for someone to make it. It's a really remarkable observation. Okay. Now we're going to get into the math of Erdős. We're going to talk a little bit about Erdős. So here's a pretty complicated definition. The KK Ramsey number is the least n such that any edge coloring of the complete graph, so this is a complete graph, by 2 colors contains a monochromatic something. Oh, sorry, this should be complete. Yeah, so not cycles, complete graphs. So for example, we've got this thing, 3, 3 is equal to 6. Has anybody seen this before? Oh my gosh, I get to blow all your minds. Yes, perfect. This is great. Okay, so you're all in way over your head right now, and that's fine. Beautiful. Okay, so check it out. So Ramsey theory is really nice area of math. If you know Tim Gowers or Terry Tao, they work on this stuff. Okay, super duper beautiful. What it's saying is that we're going to color the edges. Okay, so first off, I need to tell you what a complete graph is. Okay, on 6 vertices. Okay, so the complete graph on 6 vertices has all possible edges. So I'm going to draw those in over here. Right, so it's got all the possible edges between all the vertices. Okay, that's the complete graph. And what Ramsey's number says is we're going to color the edges of this thing by 2 colors. We're going to color some of them red. And we're going to color some of them blue. Okay, and we're going to color all of the edges of this thing. And we're asking how many vertices do we need so that we always have a monochromatic triangle? So, right, so this is a monochromatic, oops, C3, and this is a monochromatic C3. And one of the first examples, or one of the only examples where the calculation is nice, is that C33 is 6. So this is saying that any complete graph with more than 6 vertices, so I'll write this down. Okay, so any complete graph with 6 or more vertices has the property that any coloring will contain a monochrome triangle. Very, very nice result. So I'll show you the nice direct proof of this to give you a sense for how the arguments go in Ramsey theory. Oh, this is such, oh, I'm so glad to be sharing this with you. This is the kind of thing that, like, if you do contest math, right? If you do Putnam, or if you like are a big dork and like reading Wikipedia, this comes up everywhere. And it's like, it's just the nicest math argument. It's like one of like my favorite arguments. Okay, so check it out. So we're gonna pick a vertex. Let's pick this guy. And how many edges come into that vertex in the complete graph? Well, 1, 2, 3, 4, 5. Okay, now we've got five edges, and we need to color them in 2 different colors. Right, so 5 edges we're going to split into 2 colors. So 3 of them are going to wind up being the same color. So let's assume it's these guys, and they all come out red. Right, so we just use pigeonhole there. So by pigeonhole, okay. Oh yeah, Harshit's getting it. Harshit's like 1 step ahead. So if this edge is red, then right now we've got our red triangle. If this edge is red, then we've got our red triangle. If this edge is red, then we have a red triangle. So if one of these guys is red, we're good. If they're not red, they have to be blue. If none of those things happen, they all have to be blue, and there's a blue C3. Right, so any coloring of this graph will produce a, either way we get a triangle. Yeah, nice. Super duper duper lovely kind of like math 102, math 202 kind of argument. Absolutely beautiful. So, oh yeah, and there's kind of a way that you can make this into a game, by the way. Again, this is something for another talk. So you can make a game out of this, and it's like way harder than tic-tac-toe. I encourage you to try this. How was how was pigeonhole principle used here? So yeah, what are the pigeons? What are the holes? 5 edges, 2 colors. Right, yeah. So yeah, so that move, that those things have to be all red. Cool, nice. Yeah, so there's a game you can play way harder than tic-tac-toe, where one player colors these edges red, and the other person colors these edges blue. And whoever makes a triangle loses, I think. So this is a game called Sim. Anyway, check it out on Wikipedia. It's kind of fun in sort of like a math dork kind of way. Okay. So now we're going to use the probabilistic method to show that these grow exponentially in K, so that these numbers have to grow really fast. Okay. I see that we're getting close to time. We've got like 10 minutes. Do people have time commitments immediately at 3? Does anyone have to leave immediately at 3? Okay, I've got 2 no's, 3 no's. Okay, Nada. Yeah, Misa is in. Okay, cool. Because it's possible to rush the end of the talk and it still makes sense, but okay, cool. Groovy. Okay, people are feeling it. Okay, so here's the crazy idea. So Erdős had like lots of really original ideas in mathematics. This is one of them. We're gonna just do it randomly, right? It's easy to generate a random coloring. We just flip a coin. If it comes up blue, we color it blue. If it comes up If it comes up red, we color it red. Okay, so in the complete graph, we've got n choose 2 edges, right? We have these guys, every pair of them defines some edge. Right, so we get n choose 2 edges. Groovy. Now, we're going to choose a subset of those vertices. We're going to choose a subset of k of them. And that's going to define some complete subgraph for us. Right, so we have, oh, this is just going to live there. Hide video panel. Oh, now I can't see the videos. Okay, so just like we did with heads and tails, we're going to say that this random variable should be 1 if the complete graph is monochrome, and it's going to be 0 otherwise. So what do we have? We have this complete graph, and we're going to look at each triple. Right, so this is going to be an S3 for us, or this would be another S3. And we're going to say, we're going to look at those 3 vertices, and in those vertices, there's going to be some coloring. Right, so here we're going to say, okay, this is not monochrome. We're going to give that a 0. And this one is monochrome. It's monochrome red. So that's going to be a 1. So what we're doing is we're splitting up the monochrome triangles according to this function x, right? This random variable x. And now we're going to calculate an expectation of this thing. So the expected value is just the probability that this thing's monochrome, right? So this is like 1 if this thing's monochrome, plus 0 if this thing is not monochrome, right? So that cancels down and we just wind up with this term. Okay, so what do we need? Well, we can be monochrome red, right? All of the edges come out as red, or all of the edges come out as blue. Right, those are the 2 ways that something can be monochrome. And if we group that together, this is going to be 2½ k choose 2. Right, so we get something like this. We can rewrite this as 2 to the 1 minus k choose 2. So that's the expectation that a single part of this thing is monochrome. And now what we're going to do is we're going to look over our whole graph, and we're going to break up the number of monochrome triangles into this kind of linearity of expectation thing. How many monochrome things can it have? Well, the total number is going to be just the sum over all of these SKs. Right, so we're going to look at every subpart, and we're going to say, is that subpart monochrome? So we add up all of these expectations. That's going to be less than the total number of subsets. So this is the total number we have the total number of k subsets of vertices. Okay, and how many k subsets are there? Well, just n choose k. So there's a lot going on here. Are there parts of this calculation we should chat about? So what I like that's going on here is we have this big expectation that's like it's looking for these complicated substructures, right? We've got, you know, some graph, and we're looking at all these subparts of the graph. And what we do is we just add up each one. So this will be like, you know, one SK, another SK, another SK. So we just look at each of those subparts. And what we wind up with is an estimate. We wind up estimating this thing. And now this is something that we can plug numbers into. We can like calculate how many of these triangles we expect to be monochromatic. Here's a key observation. If the expected value is less than 1, then it has to be 0 somewhere. So if we can make this number less than 1, then there's going to be some coloring with no subtriangles. So like, right? And this is kind of a common sense idea, but it's a very key observation, right? If you look, you know, if you're in a class of people and the average of the class is less than 100%, there has to be someone in the class who did not get 100%, right? Or if you look in a group of people and the average number of children is 0.5, then there has to be someone without children. So here we're looking over all colorings and we're saying if there's a coloring with expected value less than 1, then there's a coloring with no monochrome triangles. And this is something where we have a lot of control now. Now we can figure out which numbers work in here to make this thing less than 1. Okay, so we're going to need a couple estimates. Nice, yeah, Nada, feel free to check out the thing later. Yeah, totally. We're going to need a couple numerical estimates. So n choose k, you can bound this as follows. Right, so you can make this less than n to the k over k factorial. And k choose 2 is bigger than a half k squared. Right, so these are like nice things about inequalities. Okay, so what we're going to do is, so this is Erdős's big idea, is to pick n in this way, and we're going to get the following estimates. So from our previous slide, we have that the expected number of triangles is like this. We're going to replace this k choose 2 with a half k squared. right? So that's using our first estimate. And this is using our second estimate. Okay. So what we're doing is we're like using these kind of like big estimates that throw away a lot of information to simplify this to something kind of nicer. Now we're going to take our actual value for n, plug that in here, and notice now everything is in terms of k's. Right? What we're going to do is we're going to figure out what properties of k make this less than 1. So these guys, okay, no worries, Harshit, that's fine. Those k squareds cancel out. We're left with 2 over k factorial. And because k is bigger than 3, this is less than 1. So what is this saying? This is saying that if n is of this size, oh yeah, sure. Actually, yeah, that's a good observation, Harshit. This can actually be equal to. Is there any significance for picking that? Yeah, it makes the calculation nicer. So if n is equal to this, then there is a coloring right? So yeah, we could pick, Brian, we could pick something that grows faster. The reason we pick 2 to the k over 2 is because the simplification happens nicely. It's so that these guys cancel out. Yeah. So what this is saying is if we have a lot of vertices, if we have exponentially many vertices more than k, nothing would work less than, that's a good question, Harshit. I don't actually know. I think we want things bigger than this. I think to make a better theorem, we want faster growing things. Yeah, so Harshit, we want to see if there's arguments that push this higher, push this bigger. And I don't know if any off the top of my head. That's something I should follow up on. Beautiful. So this is crazy. So this is saying if you want a coloring with no monochrome CK, just toss a coin, just make a huge graph and flip coins randomly. And that will produce the object you want. And this is very different than what mathematicians used to do. Mathematicians used to always come up with really explicit constructions, really like do A, then B, then C, then D. And what Erdős is saying is like, just try random stuff, just like do whatever, and it'll probably do what you want. It's a really different way of thinking about mathematics and a really beautiful one. Awesome. So there's a way to get at this via counting. I'm going to leave this in the slides. there's a nice direct Math 202 way to do this by counting. But I want to just say where this stuff comes from. So this paper of Erdős came out in 47, pretty recent. And the book that just like covers all this stuff, especially the algorithmic aspect, is a totally awesome book, The Probabilistic Method. The stuff that we talked about today is example 1 in that book. Okay, so they go into a lot more detail than what we've done today. This has just been an introduction to the probabilistic method. I'm going to be talking about this material next week, in fact, at what's called undergraduate seminar. And it's exactly the sort of thing you're doing here, except we're advertising on Twitter. We're advertising to lots of different people all over the world. And it's a wonderful opportunity to give a talk. Brian gave our first talk last week and just nailed it. It was awesome. And it was cool. A real world expert came out and saw Brian's talk. So it's a good way to get yourself out there to talk a little bit. And the kinds of talks that you're giving in this seminar would fit really well, or sorry, in this reading group would fit really well with the seminar. I know we're a bit over time. If people have questions and want to stay around and chat, I'm happy to. I'd love to talk more about this stuff. So thank you for listening. If you've got questions, please let me know. Oh, clapping. Yay. Thank you. Thank you. Thank you. Thank you.
Awesome. Thank you for the great talk. I just want to add on one thing. If anyone's interested in talking in Parker's undergrad seminar, feel free to use this reading group as a practice platform, because this happens on Saturday and the seminar is on Wednesday. So you could use this as a practice, and then you can go there and then to give the same talk again, but better.
Yeah, we're super duper okay with that. That's what I'm doing today is I'm trying out this probabilistic method talk. And now I know, okay, I'm a little bit over time, so I have to cut a slide or two. So yeah, feel free. We'd absolutely love to have more undergraduate speakers. If you want to volunteer, just shoot me an email. And yeah, I'd be happy to chat about possible topics. I'd be happy to see whatever you're doing here. I want to attend this reading group more because I think you're doing really cool stuff. Yeah, any questions, any thoughts about this stuff? So yeah, you can do probability with graphs. You wind up with these really, really cool probabilistic constructions. And it's a really wacky idea due to Erdős. He really, really pioneered this method and used it for all sorts of stuff. One of the research problems that I really want to work on is using this probabilistic method in game theory. So Erdős uses stuff for constructing graphs, and you can also use it for constructing optimal strategies in games. And I might come back at some later date, if Brian lets me, and give a talk about how this stuff connects to game theory.
Oh yeah, definitely. Just let us know how that goes. And yeah, sounds super exciting. Yeah. I think like the first 20 minutes of this talk, it's relatively a lot easier to follow compared to the second half once we dive into Ramsey theory. Yeah,
the first half was like very elementary, and so like up until, let's see, up until here, I think things were pretty good. And then after slide 11, things get pretty intense. Yeah, so you think I should smooth things out a bit, slow things down a bit?
What do you think if you, I guess, like spend a bigger proportion on the second half? I'm not sure what everyone here thinks, but
Yeah, what do people think about rejigging the talk a little bit? Because I think Brian's right.
I guess it also depends on the audience. If the student hasn't taken, for example, any stats course, I think it's still a fair introduction.
Yeah, second half is more heavy. Second half is like. Yeah, I'm gonna give the slides to Brian. Do you want them annotated or no annotations?
I think annotated will be better. Yeah.
Okay, cool.
Yeah.
Cool. So I'm going to hand these off to Brian. I get the sense that the videos go up on YouTube.
Yes.
Okay, cool. Well, let me know when the video's up. I hope to come and visit this reading group again. I think you're doing a really cool thing here. Thank you for sticking around, even though we went over time. And I hope that you have a lovely end of Saturday, and I hope you have a lovely Sunday. So thank you very much, folks, for sticking around.
Yeah. Thanks again for giving the talk. It was super interesting. Awesome. Bye, everyone. See everyone next week.